defetto, product locale, quarto rate, si Sophie
Okay, cool.
et où auditorium too.
Okay, I guess we'll just start and maybe more people will turn up. We'll see how we go. But welcome to week 5 of our space-time course. Today we're going to be discussing the arrow of time, so direction time. And I couldn't resist with this one, so I've got an arrow, got the sun shining, the sundials, the candle, melting down as time goes on. So there's a lot of references here. Sand, called hourglass. And this is the time will come. So basically, we've got a lot of different asymmetries in time. We've got this thermodynamic arrow, that entropy increases over time. We've got a cosmological arrow. We observe the universe expanding in time, not contracting in time. We've got a radiative arrow, so waves tend to expand outwards from their sources, like when you drop a stone into a pond and you see the waves ripple out. You don't often see the waves converging back in upon their sources. We've got a causal arrow. Causes always precede their effects, not the other way around. We've also got this fork asymmetry that Horwich emphasizes, that many later events seem to be correlated with a single earlier event, and it's not often that we see kind of the reverse of this happening. We've also got the knowledge asymmetry, which we've been discussing a bit already in past weeks. We have knowledge of the past, but not of the future, so there's an asymmetry here. We've got the deliberation asymmetry, which seems to be related as well. Our deliberations are only about actions we will perform, not about actions we have performed in the past, or actions that we could perform in the past. So. And we've also got this arrow of experience, where we have the experience of moving towards the future. So it's a lot of different asymmetries in time. What do they could tell us about time itself? Well, if we're working with the block universe of time, it would seem that there's just asymmetries in time rather than of time. So the block universe view of time treats time in the same way we treat space. So it's all laid out, all times exist. There's nothing special about the present moment, and there's no objective difference between past and future, just as there's nothing special about being located here now in space. So everything's laid out, nothing really changes on the block universe view. There's no temporal passage. So how could we explain these asymmetries we observe? Also, if all fundamental laws of physics are time symmetric, explain what this means in a minute, then why do we have these asymmetries? So another question is that, are they maybe related to one another? Could some explain the existence of others? So how? What's kind of the relationship between all these different asymmetries? So I thought as a starting point, we can at least start to kind of group these into different, that seem to be related. So the thermodynamic arrow, the cosmological arrow, and the radiative arrow definitely seem to be physical, related to our physical laws somehow. Whereas these ones on causation, they seem to be related to causal influences. So maybe we could tie, maybe there's a relationship between these sections as well. And the psychological arrows, we typically have grouped them together in the past weeks to the knowledge asymmetry, deliberation asymmetry, and this arrow of experience. So maybe some of these could explain this, or these together could explain this. There's lots of ways we can start to piece them together. So we saw last week that the dynamic conceptions of time are really motivated by our experience of these psychological arrows. So the A theory accounts of time hold that there's a real distinction between past, present and future, and that our experience of temporal passage reflects something real in the world. There is time and it is passing. And so it directly explains the arrow of experience by reference to the world where there is time passing. The growing block view incorporates the A theoretic account. It readily explains this deliberation and knowledge asymmetry. The reason we have knowledge of the past and not the future is because the past exists, the future doesn't exist. And the reason we deliberate about the future is because it's open, whereas the past is fixed in some sense. Presentism, as we've seen, it has a harder time with these asymmetries because it views the past and the future in symmetrical ways. They both don't exist. So then they have to do a bit more work to explain why we have these different attitudes towards the past and how we can explain some truths that we want to make about the past. Okay. So, on the other hand, the block universe view says that there is no objective temporal passage. Nevertheless, on this view, it kind of allows that there could be emergent psychological arrows. And we started to see some ways in which these might be explained. For instance, due to the way we our sensory apparatus and the way our minds construct our pictures of the world and the way the memories form gives us this illusion or this feeling of temporal passage, even though it might not be in the world. And I think some of these psychological arrows, the way we observe the world and view it, may be viewed as a consequence or somehow related to these physical asymmetries, such as the thermodynamic asymmetry or the cosmological asymmetry and causation asymmetry. So the fact that we observe things happening like this might be also responsible for our feeling that there is temporal passage. So you can kind of go two ways with this. You could say that maybe these physical asymmetries represent something fundamental about the world, or maybe it's just another way that we're picking up and our minds are presenting the world to us. Okay. Good. So the problem is that according to physics, there are no fundamental asymmetries in time, except for some little exceptions that we'll discuss, of course. So if there are no fundamental asymmetries, then how do we have the emergent asymmetries that we experience? So again, leading back to the main sort of questions I hope we can discuss today is how do we explain these asymmetries? If the laws are time symmetric, why? Why are they there? Why are these asymmetries present? Why do we observe them? And how we can start to relate the asymmetries to one another, explain some in terms of the others, and so on. So, depending on how we go, I'll start by explaining what we mean by time symmetric laws in physics. I'll then discuss the thermodynamic asymmetry, the cosmological asymmetry, which is related, then a bit about causation, and if we make it this far, briefly on the fork asymmetry, though I don't have too much to say about this one. Okay, good. So, time symmetric laws in physics, typically we say that a law is time reversal invariant, which is kind of a more precise definition of time symmetry. So a law is said to be time reversal invariant if, given the state of a physical system at any time t, it is possible to determine its state at any other time before or after. And the recipe for finding these states in either direction is the same. So here we've got a closed system of just two particles moving. The arrows represent their velocities. And here we've got your initial time. After some other time elapses, at time t2, they've moved up here. So the time reverse of this is having the particles reversed in their velocity and starting with this later time and then running it backwards. So the recipe in classical mechanics for doing this, basically, you define your state. The state of the system is given by the positions and velocities of all your particles in the system. And then to find the state at time t2, you just feed this in and then solve for the state of the system at time t2. If you want to find the state at time t2, which is before time t1, you feed in the positions of the particles and the reversed, so the negative velocities, and then you solve for the state of the system at the earlier time.
Could you please repeat that? I don't understand the picture.
Okay. So the recipe would be Newton's laws, and the initial state will be the positions and velocities of your particles at t1.
Yes.
You put that into the equation, you solve it for time t2, and that will give you the positions and velocities of your particles at time t2.
And you say the same recipe going backwards?
Yeah, you take but you put in your particles position and velocity again at the state that you're starting with.
If you start out with the same picture.
Oh, then it might be different. Yeah, you're right. So these two aren't really clear, are they? So starting out with the same picture, you'd want an earlier state from this. Is that what you mean? Yeah. Then you'd have.
And you should end up like picture number 2?
No, I'm taking that one then, and then calculating that as the earlier state. But if you're starting from this state and you want an earlier state, yeah, that would be in a different position. Yeah. They'd be in different positions in moment.
With the same recipe?
Yeah, you can find whatever that state is before here using the same recipe, exactly, yeah.
But it will not be identical to the second picture?
No. Yeah. So this picture would be the result of starting with this one and then saying what was the earlier state. Mm-hmm. And you end up with this picture. Yeah, I'll put more equations next time. I put one equation, but it's not not really that clear. But Newton's second law, so F equals ma. Acceleration is the change in velocity over time, velocity being your change in position over time. So you've got the second derivative here. So if you're putting in negative t, you're going to get the same answer as if you put in just positive t, because of the squared cancels out the negative signs. So in that example, it's quite clear that you're going to get the same answer whether you put in negative t or positive t. Okay, so basically if this is a solution, so this state is a solution, then so is the time reversed state. This will also be a solution to your equations for a time reversal invariant equation. So basically, if I showed you a movie of this one, say that's 10 seconds in between, and I showed you a movie of this one, and I asked you to guess which one is the movie going forwards and which one is the movie going backwards, you wouldn't be able to tell me. It's just particles moving around. There's nothing that tells you whether one is going towards the future or one is going towards the past. Yeah.
But this is because these are conservation laws, isn't it? So if it's a conservation law, it doesn't matter in which direction you're going. You can go in any direction as long as you conserve a certain. Here is the quantity of movement, isn't it?
Mm-hmm.
It's the moment.
Yeah, there's a relationship between symmetries and conservation laws. Yeah. Especially when we're talking about a closed system like this, right? So if we had an asymmetry, if it was losing energy, then it wouldn't be type symmetric, right? Had an open system. Mm-hmm. Okay. So, oh yeah.
Does the same thing apply for the other laws of Newton, like force and is the same as the negative force?
Mm-hmm. Mm-hmm.
Would that be the same?
Yeah. So, defining force in this way, that's got the T in it. Yes. Yeah. Basically, all our physical laws are actually time reversal invariant. An exception is the second law of thermodynamics, which we'll look at. Another exception is that these kind of weak decays, this is a neutral kaon and B mesons, they're only observed to decay kind of in one direction. It's not time invariant, these two. But they're CPT invariant. So if you also reverse the spatial positions of particles and conjugate their charges, so turning particles into antiparticles with the reverse charges, and reverse time, then these laws are invariant. But this is just an aside, you don't need to worry about. It's a technical thing. Alright. Point is that all our laws, except for these, and the thermodynamic entropy, are time reversal invariant. So this includes special general relativity, Maxwell electrodynamics, quantum mechanics, and so on. And yet, the world we observe is obviously not time symmetric. We see things falling into decay, like this one. It's meant to be paint chipping and peeling off of a wall. We see things break spontaneously, but not spontaneously rearrange themselves, and things like this. So many of the asymmetries we see might be related to the second law of thermodynamics, which isn't time symmetric. So, go on to explain what this means. So, thermodynamics, it's a theory, or rather a branch of physics, that describes the transfer of heat and the thermal properties of liquids and gases. And it was developed in the 19th century to describe steam engines. And what it described are just macroscopic quantities. So macro states are ones defined in terms of macroscopic quantities, such as heat, pressure, volume. So this is an example of a steam engine. It uses steam to drive a piston, which moves, I think, this arm, which in turn causes the wheel to rotate. So you're using the thermal energy of the steam, the heat, and you're converting it into mechanical work as this rotates. So the second law of thermodynamics, you can frame it in different ways. One way is stating that there's no process whose only consequence will be the transfer of heat from a cold body to a hotter one. So heat only goes from hot to cold rather than from cold to hot. Another way of framing it is in terms of entropy, which says that the entropy of a closed system never decreases. There's also a formulation that describes the relationship between heat and work, but I didn't put this one up as well. Yeah. So working with this formulation in terms of entropy, well, what is entropy? There are actually several different definitions of this, but for our purposes, we just characterize it as a measure of disorder. So the more ordered a system is, the lower its entropy, and the more random and disordered it is, the higher the entropy. So for instance, this system, it's closed in the box. It's a low entropy if the particles are arranged in a very specific configuration. It's high entropy when they're all spread out. And so things naturally tend to spread out like this. The same here with your coffee. When you pour the milk into the coffee and all the milk particles are just in one little area, that's a very low entropy state. But then as you watch it, they'll all start to spread out and disperse, and they'll eventually arrange themselves into a high entropy state. So you never see the opposite happen in a closed system. So you'll never see all the milk particles spontaneously just go back into this configuration where they're stuck in one little area of your coffee. So it gives us an asymmetry. If I were to play this one to you forward and backwards, you could immediately tell me which way is going forward and which way is going backwards. Okay. So maybe that can start to give us some of the explanation of asymmetries that we observe. The problem is that thermodynamics and the second law along with it isn't fundamental. So it was shown to be reduced to statistical mechanics. And statistical mechanics is a micro theory. It describes tiny little particles which buzz around into each other, just obeying classical mechanics. So it takes these macroscopic quantities and macro states, pressure, temperature, volume, and instead just describes the positions and velocities of all the little particles and averages out over these. So because it's obeying classical mechanics, these little particles, the theory is time symmetric. We seem to lose our second law asymmetry. So just as a quick aside, this was developed by Ludwig Boltzmann at a time when people didn't know and didn't believe in the existence of atoms, but he conjectured and showed that we could explain these properties in terms of the behavior of particles and atoms. And a lot of people really thought this was pretty bad philosophy to be postulating these unobservable little entities buzzing around. So Ernst Mach, who we'll be discussing in some later weeks, was really against this and was quite a rival to Boltzmann's views. All right. So, briefly on statistical mechanics. They said it's a statistical theory. So it describes particular macro states in terms of micro states. And a given macro state is more probable, statistically more probable, if it's associated with many different micro states. So many different ways in which the atoms can be arranged, that when you average out gives you the same macro state. The microstates themselves are all equally probable. So the system, it's going to go through this state, it's going to go through this state, it's going to go through every other little state. The particles are just buzzing around chaotically, and given enough time, it will go through all possible configurations. So because there's more ways for the system to be disordered than ordered, then any system that you encounter at any time, you're likely to find it in a state of very high entropy. but there will be fluctuations. As I said, the system goes through all possible microstates. So it's possible, but very, very unlikely, that when we stepped into this room today, all of the air molecules are all concentrated in one corner. It's going to go through that state eventually. All right. So a system in a very low entropy state, so a very unlikely state, where all the air is concentrated in this corner of the room, is very likely to evolve to a higher entropy state. The problem is that it's also more likely to have evolved from a high entropy state. If we see all the particles in this corner, it's likely that a brief moment before they were spread out. So again, we've still got this symmetry here. We don't have an asymmetry that would give us the second law. So why do we observe only entropy going in one direction? Well, Boltzmann's suggestion was that we're in a fluctuation. So the universe as a whole, statistically speaking, it should be in a state of maximum entropy, meaning everything's spread out, there's no change. It's called the heat death of the universe. It's an equilibrium. Without having this entropy gradient, there's no way you can make things happen. There's no way to convert heat into work, for instance, and the universe is dead. But there will be small regions, he says, where they have lower entropy, little fluctuations. So this is meant to be the whole universe, and these are little fluctuations that occur for very short time scales compared to the age of the universe as a whole. So this is quite a multiverse picture. We just happen to be here in this very big fluctuation. And so Boltzmann appeals to what we now call the anthropic principle. Creatures like us could only have evolved in a region that started off with low entropy and where entropy is increasing. So it's not surprising that we find ourselves, therefore, in a region where entropy increases. Wherever there are observers like us, there will be an entropic arrow. The problem with this view, which was pointed out by many people, but nicely put by Eddington, is that fluctuations are very rare, and the bigger fluctuation, the more rare it's going to be. So it's overwhelmingly more probable that we're in kind of the smallest possible fluctuation consistent with human life. Except he doesn't say consistent with human life, he says consistent with the existence of mathematical physicists. So a universe containing mathematical physicists will, at any assigned date, be in the state of maximum disorganization, which is not inconsistent with the existence of such creatures. So Boltzmann would put us in this giant fluctuation where we have the whole universe existing. Well, he didn't know the age of the universe, but close to 14 or 13.7 billion years. That's a big fluctuation just to explain us. It's more likely that we're in this little tiny fluctuation, which occurred maybe 5 minutes ago, that is just a disembodied brain that's just imagining that mathematical physicists exist. So we're all just in the imagination, a dream of this Boltzmann brain. So that's what the theory tells us. And so, yeah.
But on the other hand, the universe is not, the matter in the universe is not spread out. We have the planetary systems, we have the Milky Way, we have all the galaxies.
Right, exactly.
Even,
We're in
even
low,
bigger
that's low
systems. So there's a kind of order in all that.
Yeah, exactly. We're in a low entropy state. If the universe was in a high entropy state, you'd expect all the particles, the planets and stuff, to just be tiny particles and radiation spread out evenly everywhere.
Yeah.
It's
so
quite ordered.
But will the theory then say that in the future the planetary systems and the galaxies and everything will be spread out?
Exactly. Yeah. Yeah.
Not the other way around.
No, not the other way around. If you have this second law emerging, yeah, entropy is increasing, yeah, we'll go eventually towards this heat death where nothing's happening. There are no stars, there are no planets, just particles spread out through empty space.
Well, I'm just thinking when I'm looking like at that fluctuation going down, like the
Oh,
entropy
yeah.
is kind of like decreasing on the way down.
On the way down, yeah.
Which,
So.
I don't know, I'm thinking, yeah. It's a long discussion.
Yeah. So I put us here.
Yeah.
So we're observing it increase. But you're right, if you were here, you are the type of creature that you are, you'd probably say the arrow is increasing that way. You'd always kind of align with the entropy. You're growing old as the universe is growing old, something like this, yeah.
So is the Big Bang kind of in the bottom of that
Yeah.
valley?
Yeah, I think that would be the idea. So it's Big Bang down here.
But wouldn't you know more about the time before Big Bang if it was like low entropy right before Big Bang, kind of?
So I'm about to come to this. Yes?
Another question. The fluctuations, how can we say that it's all leading towards a state of max entropy when there keeps being fluctuations here and there? Like can't there just be another fluctuation at some point?
Exactly, yeah. Exactly. That's it. Overall, this is maximum entropy and there are all these little fluctuations. In order to explain why we only see entropy increasing, we have to suppose that we're in a fluctuation. Well, according to Boltzmann, that's one explanation. The point is that this explanation doesn't seem to work because of this reason. So instead, another suggestion is, just as you were saying, the universe just began in a very, very special, very unlikely low entropy state. And actually, according to the currently most accepted theories of modern cosmology, this happens to be the case, or we require it to be the case. We believe in this Big Bang. We don't know what goes on here actually because our equations break down here. So it's a convenient place to put stuff we don't know about, right? Yeah, it could be super, super low entropy. And we need it to be super, super low entropy. So it was low entropy. So after the Big Bang, the universe undergoes inflation, where it rapidly, exponentially increases in size, like here. And then it kind of remains steady for a while, increasing. And where we are now, we actually observe the universe is not only increasing, it's accelerating as well. So yeah, it seems like the universe is on the way to heat death as everything spreads out. Yeah.
But isn't the Big Bang theory saying that it was high entropy before Big Bang? Or was it low?
It doesn't say anything about before the Big Bang. All it talks about, it doesn't say anything either about at the Big Bang either. It just kind of says after the Big Bang, in a few seconds afterwards, the universe, was very specially organized in a low entropy state.
So this is theory about the time glass thing, but high entropy and then the Big Bang very low entropy.
Yeah, there are other cosmological models. Yeah, physicists are working on them, especially ones compatible with quantum gravity. That may replace this picture and give us an explanation. But at the moment, this is the best we've got. So people are working on getting a more complete picture, which might, hopefully give us an explanation about why this was a low entropy state. But at the moment, this picture itself doesn't make the initial state any more probable. it kind of makes it worse because it says that we really, really need this initial state to be low entropy.
This is a nice picture, but a big bang, wouldn't that bang in all directions? Not just like this?
So it bangs the universe into existence, right? I know, it's the way it's got light radiating out here.
Since it's directed towards the right hand side here.
But could that be like a four-dimensional representation?
Yeah, exactly. It's a consequence of the depiction. It's banging out throughout the whole universe in all dimensions. Alright, so our universe is expanding, and it's expanding in times as moving away from the Big Bang. So we have this cosmological arrow, and by definition, it seems like it's just aligned with the entropic arrow, where we've aligned ourselves to the entropic arrow, and we've aligned the cosmological arrow in this way too, by definition. As we were saying, yeah, we're currently in a low entropy state. We have all the heat concentrated in very special configurations of stars, which are separated by cold, empty space. In a high entropy state, we'd expect all this space to be full of radiation. And that's where we're heading. You know, the sun radiates the Earth, and then the Earth gives off the heat, and it becomes random thermalized radiation going off into the emptiness. So we're moving towards equilibrium, which would be the heat death of the universe. Okay. So I couldn't resist putting this one in, which was in the book. So we've looked through the window onto the world provided by the second law, and we've seen the naked purposelessness of nature. The deep structure of change is decay, and the spring of change in all its forms is the corruption of quality of energy as it spreads chaotically, irreversibly, and purposely in time. All change and time's arrow point in the direction of corruption. The experience of time is the gearing of electrochemical processes in our brains to this purposeless drift into chaos as we seek into equilibrium and the grave. So I think that gives us the picture.
Plato.
No, by Atkins.
Yeah, but it's Plato.
Plato says this too.
Yeah.
Alright. So the next question is, of course, does it really explain all of these arrows? Does it really explain all of the asymmetries in time, our psychological ones, the causation, and so on? For instance, can it explain the knowledge asymmetry? Well, Hans Reichenbach says yes. So the knowledge asymmetry, why we have knowledge of the past and not the future. You're walking on a beach and you see a sandy footprint in the sand. The sand itself, all around here, it's all spread out randomly, it's flat, it's at a high entropy. The footprint itself is a special configuration, it's a very ordered imprint, and so it's low entropy. And so you infer naturally, not because you know the second law, you've internalized the second law and aligned yourself with it, you know that it's really unlikely that you'd find the beach in this way on its own. It wouldn't randomly fluctuate into this. Well, it would, but not, you're not likely to find it there. So you infer that the footprint was made by an external influence. It's not a closed system anymore. A person was walking there in the recent past. So it's given you the asymmetry. You know that something has happened in the past because it's left this mark. The problem is that this doesn't really explain why you've inferred to the past. Why not infer that it was made by a person walking there in the future? Seems like you've already put in the asymmetry here. The reason is because you've had to assume an external influence anyway, so it's no longer a closed system and you can't just say entropy is going to increase. So it doesn't seem very justified to think already that it's coming from the past and not the future. So we need kind of something extra in this case. That something extra may be a sense of causation, your idea that causes always precede the effects. So very briefly, the arrow of causation is, the idea that causes always precede their effects. Could this be the fundamental arrow that explains the others? Well, me personally, I think it's probably not fundamental, but I don't think that rules out it being explanatory, especially in the case of asymmetries. So I would kind of leave that up to you if you think that it can play a role in explanation. I think kind of the game today will be how we can audit the arrows and see which one relies on which. But why would I say that I don't think it's fundamental? Well, firstly, as we've seen, there's nothing in the physics that distinguishes between cause and effect. Also, it seems like we shouldn't automatically rule out backward causation. It could be that there are causes that occur in the future of their effects. For instance, in some interpretations of quantum mechanics, and also if we want to or believe that time travel is a possibility where a cause in the future could influence something in the past. So there's reasons to maybe not kind of stipulate from the outset that this is the fundamental asymmetry. So I'm kind of, Hume said this as well. I visited Hume in Edinburgh, 2 Humes. This one's a bit weird because he's just wearing a toga. But Hume says famously that we never see causation as a something necessarily happening. What we see is just one event being followed by another. So you hit the white ball hits the yellow ball. You see the white ball move and you see the yellow ball move. So we always have seen one event following another, the yellow ball moving after the white ball hits it. We infer by induction, based on all these past cases, that the next time we see the white ball hit the yellow ball, the effect that the yellow ball will move will happen. So we just suppose this via induction, based on all these past instances. And we suppose by custom that the future will always be conformable to the past. So there's different interpretations of Hume on this. One interpretation is that the causal asymmetry is not to be found in nature, but it's something we project onto nature. We infer it, and so we codify it. We then write down our laws. We write down Newton's equations. But these equations are just kind of codifying what we believe is happening in the world, our projection onto the world. Okay. So it's possible that the next time you see it, it doesn't follow. And this GIF is like really frustrating because it's just like that the whole time. But it's, that's it. You're inferring. You already know what's going to happen. You know, you're projecting that you're going to hit the white ball and then the yellow ball is going to move. Good. So I think I'll just leave it there. Maybe just another comment on the causal asymmetry. It's kind of stepping aside from Hume on this point, because he'd probably say that this is true of all our physical laws. They're just codified things that we're projecting. But stepping away from that, you might think that taking the entropic arrow as fundamental might be one of the reasons that we do see one effect as always following from a particular cause. So you could perhaps explain the causal asymmetry in terms of the entropic asymmetry. The reason why we see this and then we see this may be due to the entropic arrow. So, okay, good. We'll leave it there. Thank you. A break for 15 minutes.